Wave propagation, sky waves, part 1, series on antennas and wave propagation, lecture number 6.14. Sky wave propagation is one of the three principal modes of wave propagation. It belongs to the category of beyond the horizon type of propagation. Wave assumes this form when its frequency falls within or in the surroundings of HF band. In the present session, which is the first part on sky waves, various aspects pertaining to sky wave propagation, they are all described. Ionosphere, which is upper portion of atmosphere, plays an important role in sky wave communication systems. In addition to various aspects of ionosphere, we also discussed how ionosphere is able to provide and affect a sky wave communication link. Let us begin the session with a short introduction on sky waves. The waves that arrive at the receiver after reflection, actually it is a refraction, or scattering by the ionosphere, are known as sky waves, or alternatively as ionospherically reflected and ionospherically scattered waves. In this first para, a definition kind of thing is being given for sky waves. Waves that arrive at the receiver after reflection, in fact it is a refraction, or scattering by ionosphere. Ionosphere is atmosphere whose height ranges from 50 kilometers to 1000 kilometers. This area of the atmosphere refracts back the wave towards the receiver. The waves that fall in the HF band and sometimes frequencies slightly above and below also fall in this mode, follow this particular mode. If the wave is far below HF, it is ground wave. If it is above HF band, far above HF band, then it is space wave. If the wave is within HF or in the surroundings of HF, then the wave assumes sky wave mode. Like ground waves, sky waves provide a means of beyond the horizon communications. Space wave mode requires line of sight conditions, whereas ground waves and sky waves, though they don't require line of sight conditions, so they are able to provide beyond the horizon communications, ground waves as well as sky waves. Line of sight conditions means the antennas, transmitting antenna and receiving antenna, if they are able to see each other, then we say line of sight conditions exist. Those conditions are not required as far as ground wave communications or sky wave communications are concerned. Even though long distance ionospheric propagation does not have the stable characteristics of a short distance ground wave propagation, it does in general provide a predictable and usable means of radio communication. Sky waves are also able to provide us predictable and usable means of communication, wireless communication. Here is illustrated the three principal modes of wave propagation, their salient features: ground wave, sky wave, space wave. ground wave below HF, sky wave HF, space wave means above HF. In ground wave propagation, diffraction plays an important role. In sky wave propagation, refraction plays an important role. In space wave, reflection plays an important role. All the three are shown in this diagram. Here is transmitting antenna, here is receiving antenna. A sky wave link is shown here. In this link, transmitting antenna is looking towards the sky. Receiving antenna is also looking towards the sky. Transmitting antenna emits a wave. If the frequency of this wave falls in HF band, it travels towards ionosphere. There it gets refracted and turned back by the ionosphere towards Earth. It travels back towards the Earth. And if we place a receiving antenna in the path of the wave that is coming back towards the Earth, then it can be received. Communication link gets established. So this is sky wave link, sky wave communication system. In this diagram, one can see also surface wave. Surface wave is ground wave. When antennas, transmitting antenna and receiving antenna, they are located near the surface of the Earth, then what happens is the wave simply falls over the surface of the Earth. There it gets diffracted, travels along the surface of the Earth and reaches the receiving antenna. We discuss at length about this mode when we go to ground wave propagation. This mode, as already mentioned, it occurs when wave is below HF band. Another mode is also there, space wave mode. This is transmitting antenna, this is receiving antenna. Transmitting antenna emits the wave. A part of this wave travels directly towards the receiving antenna, reaches the receiving antenna. It is called a direct wave. Another part hits the surface of the Earth, gets reflected there and reaches the receiving antenna. So there are two parts mainly. One is direct wave, another is a reflected wave. These two together constitutes space wave communication link. A description of space wave link has already been given in another video session. As already mentioned, space wave, it exists when the wave is above HF band. In the present session, our focus is on sky wave, ionosphere, related matters. Now, sky wave propagation. The wave propagation in ionosphere is a rather complex phenomena. In the ionosphere, the constituent gases are ionized. That is why it is called ionosphere. What is ionization? Atoms, as they are electrically neutral. If we remove one or more electrons from it or add one or more electrons to it, then the neutral atom becomes ionized. Ion. If it is neutral, it is atom. If it is charged, then it is ion. That is the difference between ion and atom. The gases in the ionosphere gets ionized, forming plasma due to various types of radiations from the sun. A plasma is a charge neutral gaseous assembly of atoms or molecules with enough free electrons to significantly influence wave propagation. So gases, atoms or molecules exist. Radiations come from sun. These radiations are highly energetic. Because of the energy carried by these radiations, electrons come out of these atoms or molecules. Now what we have is ions plus electrons. This fluid is called plasma. The ionosphere exists in Earth's magnetic field B0 and hence it is influenced by it. Hence it can be considered as magnetized plasma, which is essentially an anisotropic medium. This plasma, which we are calling ionosphere, is part of atmosphere, and atmosphere is part of Earth. Earth is associated with the magnetic field. Therefore, ionosphere is in the magnetic field of the Earth. The plasma that exists in the ionosphere, it gets influenced, it gets magnetized by the Earth's magnetic field. Hence, it is called magnetized plasma. As the medium, it is anisotropic. Anisotropic means it influences the wave propagation differently depending upon the direction of wave travel. It exhibits properties which are direction dependent, direction of wave journey. As a consequence of this anisotropy, wave propagation characteristics are different in different directions in the medium, making the values of permittivity and conductivity as tensors. Some more points regarding skywave propagation. Dielectric constant of plasma is always less than unity, and it can even assume negative values. Refractive index is square root of dielectric constant. Refractive index of plasma medium can be shown as square root of 1 minus 81n over f square. This is a refractive index. Refractive index is an important parameter for us as we want to trace out the wave path. We want to analyze wave journey using Snell's laws of refraction, which is in terms of refractive index of the medium. So index is an important parameter. As far as plasma is concerned, it is given by this particular relation. Here n is steady state electron density. The refractive index of the ionosphere as well as its layers decreases as we move upwards from their bottom faces because of the increase in ionization density. Notice index depends upon n. N is electron density, but electron density in the ionosphere changes, so n also changes. The trend continues until middle of the ionosphere and its layers where ionization levels reach maximum, and beyond the middle ionization level falls, causing the increase in the index of refraction. So this is layer, let us suppose this is layer. N electron density increases as we move upwards, reaches a maximum value, and then if we move further, ionization density decreases. So n is maximum in the middle. Small n, which is index, therefore it is minimum in the middle, reaching maximum values at the end faces. Here is shown how a wave gets refracted. Wave travels, this is ionosphere. Wave travels like this, enters, it gets bent like this. Further bending happens, and it comes back. This bending towards Earth is facilitated by the fact that here n is high, index is high, and it decreases. As we move upwards, it decreases. Because of decrease in small n index, what happens is bending takes place like this, and this is in accordance with Snell's law of refraction. Sin I by sin R is equal to n, refractive index. Some more points. Refraction by ionosphere is more severe than atmospheric refraction, and the angles of refraction can be computed using the properties of plasmas. A relation connecting frequency and incidence angle with the required ionization level to return the signal back to the earth can be found. It is given here. F is equal to square root of 81 n secant phi L. The angle between the direction of the wave travel and vertical to the earth is called launching angle. It can be approximated to incidence angle phi L equal to phi I. Here he is explaining the meaning of phi L. Phi L is actually a launching angle. It is nearly equal to angle of incidence. It says, this law says, waves of higher frequencies and lower incidence angles require higher ionization levels. As higher ionization levels are available in the higher layers, the wave requires to travel deep into the ionosphere to get returned to Earth. If the required ionization density is not available in the ionosphere, the wave then escapes into space, never to return back. These are few observations which are useful for us to go deep into the phenomena of refraction by ionosphere. Similarly, waves of lower frequencies and higher incidence angles require lower ionization levels. As required lower ionization levels are available in the lower layers, the wave need not to travel deep into the ionosphere. It gets turned down to Earth by lower layers. Another aspect is wave of higher frequencies can be turned down by lower layers of low ionization density for larger incidence angles phi I, but it requires higher layers of high ionization density for smaller incidence angles phi I. The highest frequency that can be turned down by a layer for a given incidence angle phi I depends upon maximum ionization density available in that particular layer. F max is equal to square root of 81 and max secant phi I. As already mentioned, launching angle phi L is nearly equal to phi I. Notice that this relation and the relation given in the previous slide, they all are derived from Snell's laws of refraction. Now we move to ionospheric layers. The ionosphere is divided into layers based on variation of ionization density. It has been told that ionosphere is upper portion of the atmosphere. But the point that has to be kept in mind is it is not a uniform layer. In ionosphere, there exist several sublayers with different properties. Those aspects we discuss here. The four layers which have the importance from radio propagation point of view are D, E, F1, F2. In the ascending order, it is shown D, E, F1, F. Layers F1 and F2 combine to form a single layer at night. F1 and F2, these two form into one layer, F layer. The electron density varies in general with altitude. Not only in the ionospheric layer, but also in the sublayers of the ionospheric layers also, electron density varies with altitude. Within any individual ionospheric layer, electron density is highest in the middle, decreasing to lower values on either side. These are general principles of description regarding ionospheric layers. Some more points regarding ionospheric layers. At night, only the F layer carries a significant ionization. The E and D layers contain extremely low ionization levels. During the day, D and E layers become heavily ionized, as does F layer. It develops an additional weaker region of ionization known as F1 layer. The F2 layer continues by day and night, and it is the region mainly responsible for refraction of radio waves. Now, some points regarding D layer. The D layer is The innermost layer, its location is 60 kilometer to 90 kilometer above the surface of the Earth. During PCA stands for polar cap absorption events, the increased ionization significantly enhances the absorption of radio signals passing through the region. In fact, absorption levels by many tens of dB can increase during intense events, absorbing most of transpolar HF radio signal transmissions. Such events typically last less than 1 to 2 days. Points worth mentioning regarding this fellow D layer are: average height is 70 kilometers, average thickness is 10 kilometers, disappears at night. Least important from HF propagation point of view, but offers good amount of attenuation to skywave. Now E layer. Points worth mentioning are: average height is 100 kilometers, visual height remains almost constant at 110 to 120 kilometers, average thickness 25 kilometers, disappears at night. It aids MF stands for medium frequency surface wave propagation. MF band is below HF band. This layer helps surface wave propagation a little and reflects some HF wave in the daytime. It can transmit the signal up to a distance of 2500 kilometers in a single hop. At night, its critical frequency falls below 1 megahertz. Regarding critical frequency, we discuss soon, very soon. Now, another layer, ES layer. S stands for sporadic. So, ES is sporadic E layer. It is a very thin layer of high ionization density. Its occurrence is quite unpredictable. It can occur both in day and night. It does not have any role in long distance communication. This propagation occurs most frequently during summer months when high signal levels may be reached. During intense sporadic events, the ES layer can reflect frequencies up to 50 megahertz and higher. Its height is in between 90 to 130 kilometers. It occurs in the form of clouds varying in size from roughly 1 kilometer to several hundred kilometers across. The skip distances are generally around 1640 kilometers. Double hop reception over 3500 kilometers is possible, and distances for one hop propagation can be as close as 900 kilometers or up to 2500 kilometers. Regarding skip distance, we are going to discuss. For the time being, just understand that there should be certain distance, more than certain distance between a transmitter and receiver in case of skywave communication system. If the distance is smaller than this one, then link doesn't work. The minimum distance that has to be there between the transmitter and receiver, that distance is called skip distance. A few points regarding F layer. The F layer is the densest point of the ionosphere, implying that signals penetrating this layer will escape into space. The F2 layer is responsible for most skywave propagation of radio waves, facilitating HF or shortwave radio communications over long distances. Salient features of F layer. First we consider F1 layer, then F2 layer. Average height is 180 kilometers, thickness is 20 kilometers. It combines with the F2 layer at night. Although some HF waves get reflected from it, most of them pass through it. It affects HF wave by providing more absorption to it. So these are some features of F1 layer. Now we move to F2 layer. Average height is 250 kilometers to 400 kilometers daytime, 300 kilometers night time. Thickness is 200 kilometers. It is by far the most important reflecting medium for HF radio waves. It can transmit the signal up to a distance of 4,000 kilometers in a single hop. The ionization density of this layer can be up to 8 into 10 power 11 per meter cube. Now, ionospheric variations. The ionization levels in the ionosphere change day-wise, season-wise, periodically. It has already been mentioned that ionosphere is not a uniform layer. There exist several sublayers, and each sublayer exhibits its own properties. Within one sublayer, two ionization levels change. This is one aspect. Another aspect is also there. Ionosphere as a whole gets affected by the radiations from outer space, mainly from sun, SUN. And radiations from sun, they vary. So it causes changes in the ionosphere. Those aspects we study here. Ionization levels in the ionosphere change day-wise, season-wise. It also undergoes changes randomly, and all these changes are dependent upon mainly on variations in the solar radiation, solar emissions. The variations can be grouped under two categories: regular ones, irregular ones. Regular, irregular. The regular variations are also known as normal changes. The diurnal and seasonal changes that occur in the properties like thickness, virtual height, critical frequency, etc. of the ionospheric layers. The diurnal changes are due to variations in the condition of the ionosphere that takes place throughout the day due to variation of the incident angle of sun's rays. The radiation input to the ionosphere also varies quite regularly with the season of the year, resulting in seasonal changes. A plot of critical frequencies and virtual heights as a function of time of day or monthly averages of these quantities gives a reasonably good picture of ionospheric variations. We discuss about critical frequency very soon. A few points regarding irregular variations. The irregular variations, also known as abnormal changes, are due to the fact that our sun is a variable star with its output varying tremendously over a 11-year period. Irregular variations are four in numbers: SID, sudden ionospheric disturbances, ionospheric storms, polar cap absorptions, and sporadic layer. These four belong to the category of abnormal changes. A few points regarding SID. SID stands for sudden ionospheric disturbances. These are sometimes called a Dellinger effect, cause a complete radio fade out lasting from a few minutes to an hour or more. This phenomena is due to sudden and unpredictable solar flares that produce a large increase in the ionizing radiations that reach the layer. It increases layers ionization density, resulting in a complete absorption of all skywave signals having a frequency greater than about 1 megahertz. However, for the very low frequencies that are normally reflected from this layer, the skywave signals will increase in intensity, resulting in improved VLF propagation. They affect only the sunlit side of the earth and never occur at night. This is about SID. The second type of irregular variation is similar to SID in origin and effect, but its beginning and ending are more gradual, and it may last for several hours. Usually, the absorption of radio signals is not complete, and communication may be carried on a higher frequency levels. Now, a few points regarding ionospheric storms. These are caused by emission of a burst of electrified particles like alpha and beta rays from the sun. The ionosphere becomes turbulent and loses its normal stratification. The radio wave propagation becomes very erratic, and it often becomes necessary to lower the working frequency in order to maintain communication. The storms tend to recur at 27-day intervals and last for several days. PCA stands for polar cap absorption. The fourth of irregularity occurs only in the polar regions during a period of sunspot maximum. The sporadic E layer is also often included as an abnormal ionospheric disturbance. This layer helps the over the horizon communication and prevents long distance HF communications. With this, we come to an end to the present session. This session is first part on skywave propagation. Second part follows. Here it requires to be mentioned that the discussion here in the present session is mostly on ionosphere. This session can be considered as a preparatory one, but an important one to understand the functioning of a skywave communication link. Hope this session is useful to you. We meet again soon in another session on skywaves part 2.